Now, lo and behold, my covariances are all zeros. So I'm hoping I can get those correct in my model. And then I notice that my Q1 and my Q14 is very, very small. It's 0.007. In fact, the biggest one that stands out is everything is less than 0.05 except Q2 and Q3. Everything is actually less than 0.04, and there's a couple that are in the 0.03 range, but the two biggest ones look to be Q3 and Q2. Now, I would actually more ideally like to look at the correlation matrix with this, and actually we can actually look at all of them, but that's where we'll do that tomorrow. But this now gives me a measure of how far off my model is from my data. I can actually look at the matrix and say, how far off is the model from the data? Now, you can probably, just reflecting on this, you could think, wow, do I have to look at the matrix every single time? And the answer is no. The answer is no. There's actually other things that we'll take advantage of that will make it so we don't actually have to do that. Okay?
Can we back up and
of course.
Look at this one? Is the answer because all of these numbers are less than 0.0? Is there sort of a threshold?
There's a cutoff. There's a cutoff matrix that we'd want to use, but not with the covariance matrix.
Yeah.
We'd actually want to use that. We'd want to use that cutoff with the. We'd want to use that cutoff with the correlation matrix, or.
So why would we run residuals at this point?
I'm hoping that I can get the residuals. The main reason is to actually explore the matrix to see if you can see something jumping out. Now, look what happens if I actually do standardize. So if I run the standardized residuals, E-stat space residuals, comma, standardized. Now, unfortunately, there's a bit of a concern with the way this actually runs. Okay? Exactly. It's what is standardized. It's essentially saying, look, if I ask myself how far off, if I think that the terms of my matrix, that residual matrix that I have here, where I take my model matrix minus the actual data matrix, if I assume those are coming from a normal distribution, how far away from zero are we? This then standardized value for all practical purposes gives us things that we could treat like z-scores or t-scores. So the idea is if it's far away from 2, that's an issue. Well, the only problem is this is extremely sensitive to sample size, and I'm not sure if you remember, but we had over 2,000 values. So these are going to be a bit inflated no matter what we do. But the first one of this, which one appears to be the strongest one jumping out at you?
14.
That 14. 2 and 3 seems to be a problem.
So that's the farthest away from the.
That's the farthest away. That's the one. So that's where you can use using this information. Now, sorry to interrupt. The correlation between 2 and 3. 2 and 3, exactly. So
Jumps
something.
away from the model.
2 and 3 was estimated at 0.8 times 0.6. That value was an underestimation.
We are not capturing enough of it.
Right.
Of the correlation. Okay. We're not capturing enough of the relationship between 2 and 3.
Yes. Yes. I'm not sure I want to actually think about the direction, but yeah.
But relation.
Yeah.
Between the 2. Yeah.
So we're too far off.
Okay.
We're too far off.
Thank you.
Okay. Now, so there's a couple ways that we could try to fix this. So I'm going to do one right now, and we're going to do SEM. Actually, let me just bring in, so I'm going to use the command. SEM outgoing, I need to make sure I get my notation correct for this so I don't screw it up. So I'm going to add a correlated error. we're going to add a correlated error, which is covariance. So we're going to add, we actually say covariance E dot Q2 star E dot Q3. That should be right.
Put a space.
Oh, I think I need a comma. Sorry. So I think we need a comma before we say covariance. Because until it sets the model, it doesn't know what the variable is. There we go.
Can you put the command up again? I missed
Yep,
it.
yep. Happy to.
Thank you.
Okay. So now I was cheating a little bit. Stop. So I was borrowing what I typed just before, and I can get that from the command, and then it's comma space covariance, and I'm telling it to take the error dot Q2, the error from item Q2 times the error from Q3, E dot Q3. So that's the interpretation of that command.
So you're putting a correlation between the
I'm saying
what are we
these
doing?
errors.
Epsilons, I guess.
Deltas technically, but yep, epsilon is just perfectly fine in a one-factor model.
Yeah.
So you're multiplying. You're not
Well,
just
no.
You're not just inputting them both into the
No, that's
the
what
function.
that's what that notation is.
Oh.
That's how this notation turns it into that.
It's not a comma. If you put covariance parentheses,
Probably, I bet you it would probably work, but no, it's got to be a star. Yeah, it's really picky.
okay.
Yep.
Is that the notation for most of them? If I were to do correlation, it would be also a star. Okay.
Although you wouldn't say correlation for this. It would always be a covariance. I think you could even just type cov for it. All right, so I'm going to do estat residuals. And now notice what my residual error is between 2 and 3. It's actually 0. And if I do estat residuals, comma standardized, now it looks like if there's an issue, it's going to be probably with Q2 and 14. But now look at my estimate for Q2 and Q3. My residual estimate for 2 and 3 being off is negligible. It's the same as if I calculated the variances for it. So this is what we are going to be doing with Stata now. We're going to figure it out, but we're going to just spend a little time looking at models like this that we can, if we really wanted to, we could actually fill in that entire matrix with the values. And then once we have that, we can then ask, how close, how good is it doing? It's estimating my thetas, all of my parameters. It's generating a matrix that it thinks should be the covariance matrix or the correlation matrix. I can ask how close those are to each other. That's the information I can pull out of Stata to look if I really needed to get in and dig in the quagmire to see what's actually happening there. Okay, so that's where I'd like to stop for now, because I need to attend to some other things this afternoon before my next class. And then we'll do tomorrow is run a two-factor model using this data set. We'll set up a basic, well, we're going to cheat and we're going to turn our two-factor model into a prediction model. That's the easiest thing. So we can see what a single path model looks like, and then we'll set up something with like a mediation model. And the key there is to keep asking what should the correlation covariance matrix actually look like. So the other thing I wanted to check was, I think core. Let me check this because I'm pretty sure this one is the one I want. So CORR will generate the actual correlation, so it should be COV. Well, let me just type this. Let me just do it again. So what I'm doing is I'm getting the actual I might have to type more than that. Okay. Is it variance? Could be variance. All right. Well, I can get the correlation matrix. I can get the correlation matrix. So this is the correlation matrix for my actual data. So I can take this information and let's actually do it. Let's actually see. So we said my correlation was estimated to be display, let me do 0.80 times 0.86. So my correlation between items 2 and 3 was 756. My model estimates the correlation to be 0.688. So it turns out my Q2 and Q3 are actually more correlated than what my model would have suggested. All right. So this, believe it or not, is actually of all. I mean, we could go on, but seeing this once and sort of letting it simmer overnight, that moment of mental digestion to make that connection between what's actually being looked at. So if you remember the squares in our regression, that image that you have sitting in the back of your mind, you look at every single point, and every single point has a square. Now I'm not looking at every point. I'm actually looking at every value in my correlation matrix. Because technically in the correlation matrix, the diagonals are all 1, and they're going to be 1 in both the model matrix and the other. So it's really everything on the off diagonal. How closely do I get those values to each other? But it's not the same image of a square anymore. We're not trying to draw a line and make squares as small as possible. That's what we'll then talk about, the fit measures and how we assess that. That will be the next week.
So basically, if we're going back to yesterday, we had we have the S and we have the sigma hat.
Yep.
S has the data matrix.
S is the data.
So we could put data matrix equals S, and then we could put sigma hat equals this.
Yep.
And we're trying to see
how close exactly. That's exactly what it is.
I'm very visual.
That's exactly what it is. Yep. Okay. All right. I'm going to go ahead and shut this down now, and and it's good because it says my battery is low. So I'm going to shut this. I'm actually going to turn off the recording first so that does not get lost.